Okay, it's just the wrong slide. Okay, here we are. Okay, well, thank you very much for letting me talk today. And I also want to say thank you from UT for sending us these cores to scan in the first place. It was a real honor and pleasure to be part of this. When we heard about this possibility, we were very excited about what some of the possibilities are from this that might not be taken advantage, that CT would be uniquely useful for. So I've been appreciating how you've been geochemically analyzing the heck out of this thing. But some of the textural data that are in CT, you can get from CT are potentially very interesting and that have since been destroyed with the destruction of the core. Things like particle size, orientation, changes in composition with depth, whether there's a difference in porosity or compaction with depth, and also whatever we can see that looks like a soil structure. Now, in order to pull these data out, we know from our geological analyses that we need good data for this. And for us, one of the hallmarks of good data is not only well calibrated and high resolution and things like this, but also the top point there, the voxels should have the same meaning everywhere. And this gave us lots of interesting things to work on with these cores, because the challenges like beam hardening, scattering, and other scanning artifacts that came into it. So first we scanned core 73002 in late 2019. For that, you were able to extract the inner aluminum tube for scanning, and we scanned it at 100 kV in, with an aluminum filter there using a software beam hardening correction. Now, the way we did the scan was we did cone beam scans, so each acquisition would be of a certain volume of the core, and then we would just do a series of overlapping volumes in order to cover the entire thing and give us room to avoid artifacts and knit things back together. If we look at, what that might look like up close to a detector, normally you just put your detector behind that and image the whole thing. But one of the reasons that y'all send it to us is that we have uncommon ability here at UT to also gather a special acquisition where we displace the detector by a half a channel in each direction. And get 4 overlapping scans, which lets us basically super sample do super sampling, so we can use a 2048 detector to get 4096 data, which in this case meant going from about 26 to 13 micron resolution data. And Ryan's given a picture of before of how much nicer that data looks, so we're not going to repeat that. Instead, I'm going to talk more about the sausage making of actually getting these things from data from our detectors to good looking images. For example, in this case, our 4 different rotations we did required a manual rotation alignment because of the state of the scanner software back then. So we did that. Another thing we found was that when we did our overlapping by taking corresponding slices from 2 different rotations and subtracting them from each other, we could see that there were a few artifacts. First, like a rotational offset that you can see because of the shadowing effect, but also more seriously, if we look at the subtraction of the tube from itself on 2 different parts of the scan, we can see that they don't exactly match up. And what does that mean? That means that we wanted the data to look like this, but this project told us that our data looked a little bit more like this, which is very exaggerated. It's only about 77 microns off, but it's enough to slightly mess up the scan. So we, I and Romy and Dave put together a correction that would straighten that thing out for all of our core sections. So when we subtract it, we get something more like this. And we also did a correction for a slight change in grayscale from bottom to top, and we'll see evidence of that in the next scan. But that was most of the adventures for this one. Now we got core 73001 in spring of this year. And when they did some preliminary scanning down at Johnson Space Center by Scott, he could see that when on the moon, they actually overfilled this core. So this seeding element here was not able to fully contain the core material, and we had core material that was leaking out here and there. So as a result of this, they decided for scanning, they needed to leave this outer steel sleeve on, which was not good for scanning. So we started compensating by getting a slightly higher energy 190 kV and not using a filter because the steel was going to be its own filter. But we did use the same software correction for beam hardening. But if we look at a reslicing of the core and cross section, we can see some of the problems we had. So we had these little, first off, these little notches right here are because of having to redo the scan in a different configuration, but trying to match the area. There was an error in how much we overlapped things, and these little notches are cone beam artifacts that that happened because we didn't overlap quite enough. So that was sort of embarrassing. But another artifact that we have is when we looked at these images of the core at the bottom, you can see that where we have that bright, the iron tubing, the iron outer sleeve in the image, we can see this half of the image is bright and this part of the image is dark. And then so and because everything was tilted, that moved. So on the bottom of the core, this part is bright and this one is dark. And then when we go to the very bottom of the core here, there's actually a stainless steel cap over the end that was actually used for the drilling in to the moon, which brightens up everything. So we had to go and figure out how to fix all these things. So first we characterized the error by taking some radial averages around the tube, the inner core, and the outer core. And in this next image, we can see what this looks like. So the tube is in black, the inner core in gold, the outer core in red. And you can see a misfit function down there. So these notches here are because of the cone beam artifact, and some of these fluctuations, especially in the inner core, is because there's a clast in the way. But you can see it's a very uneven pattern that goes through, and then it goes sort of haywire by the time we get to that metal cap. So we had some work to do. First, we had to take out the cone beam error. So we figured out a function to parameterize that. Here's what one of the worst cone beam error slices looks like: bright in the middle, dark around all the edges. And here's what it looks like in cross section again, a triangular notch in that reslice. So we concocted that function to do it, and then we sort of semi-hand fit that function to the extent of the artifact as it goes through its little triangular notch and gets lower in magnitude and goes out towards the edge. And by doing this characterization, we could subtract the entire thing out. So we go from here on the left to here on the right to get a pretty much flat image, getting rid of almost all that artifact. Very hard to see now. So if you look on the bottom, we go from that state to this state. So still little hints of the cone beam artifact, but that's as good as we're going to do with that. So our next job was to characterize the asymmetric error coming from the steel tube and also from the wires. So if we run another radial average around the tube, we see a pattern that looks like this. It looks nice and sinusoidal, but there are multiple components, partly because we have these other metal bits casting additional artifacts out. But since it is pretty sinusoidal, we can run a Fourier decomposition. So we did this with 3 terms of the Fourier series just to keep everything as smooth as possible. If we look at those 3 Fourier components, here's the first one is the big one. The second and third are both there, trading off and sometimes canceling each other. When we subtract out, so we subtracted out that Fourier error, and you can see it's nice and flat here through the body of the core, although it's still haywire in the cap. But once we did that, we could take advantage of the fact that we have a density standard embedded in the sample, which is the aluminum tube. So we can normalize everything to that aluminum. In this case, it's the inner rim of the aluminum tube. But now you can see in our inner and outer core data that they're really not overlapping that well, and they really should do better. Once again, these bumps in the inner core are because there's a clast in the way, but the overall increased height is because of another problem. So if we do something like take 100 images and average them together, we can work out a diagram like this of mean CT number versus radial position. And we can see that we are slightly brighter in the middle than towards the edge. and we can fit a function to that. And then if we think a little bit beyond the edge of the dirt, we can see that this actually continues off into the tube, and we can see that the inner part of the tube is a little bit brighter than the outer part of the tube. So that's actually continuing the same beam hardening error. In this case, what happened is the beam hardening correction we put on was a slight overcorrection, because the normally beam hardening would be dark in the middle and bright on the outside. We put in a correction to flatten that, but we went past flattening it and overcorrected by just a little bit. But it was impossible to see earlier because of the metal, the iron artifact overprinting absolutely everything. So once we parameterize that and subtract it out, our inner versus outer looks like this, and we get a really wonderfully flat image where we are actually living up to our standard of those voxel numbers meaning the same thing wherever you are in the core, at least for part of it. However, there's still the issue of what to do in the outer part, under that metal cap. So we went back in once again and parameterized and sampled and tried to parameterize the air due to this metal cap, the iron cap for drilling. And we could see that the bigger the metal, the thicker the metal was, the worse the artifact was. And we could even see in cases like this that in areas where the metal was notched because of just the way it was put together, the artifact is less severe past the thin metal and more severe past the thick metal. So we had to come up with a radially varying correction that would take care of that. And here's some before and after pictures. Here's before, and here's after we subtracted out those errors for the beam hardening in the cap. And you can see that the inner and the outer are matching each other pretty well and doing pretty well at matching the rest of the scan as we went down. So we think we did a pretty good job at that too. Now, this all took a while, so there's always more that we could have been doing, but Ryan was calling about 3 times a week by this point, asking when they can get the dang data so they can take apart the core. And I had to stop taking my spare time and going down to the lab and puttering away at this. So we had to stop someplace, but there are still some artifacts that are left that if anybody's going to use these data for this kind of purpose, like trying to infer soil densities for porosities, you need to keep these kinds of things in mind. For example, these beams right here, these are scattering artifacts because of the thick metal and the change in thickness of the interface, certainly a scanning artifact. Another thing to keep in mind is actually our beam hardening correction on the new scan was is actually better than it was on the first scan. If we really contrast up the first scan of 73002, we can see that the outer part of the metal is a bit darker than the inner part, and this class of the same material is a little bit darker in the outer than the inner. So a very, very slight overcorrection, not as bad as it was for 73001, but there's a little bit of, there's a little bit of an issue there as well. So in other words, we are very proud of these data, and we're looking forward to being able to use them, or other people being able to use them for these textual analyses, but use with care. And that's the end. So